Good evening, dear all. Let us continue the topic of electric dipole. We have already learned what happens when an electric dipole is placed in a uniform external electric field. Today we will place the dipole in non-uniform external electric field. Now the representation of uniform electric field is parallel lines equidistant to each other. But what is the representation of a non-uniform electric field, or what does it actually means, that we will understand first. Then we will place a dipole in the non-uniform electric field and find out what will happen. Okay, so first of all, let us understand what is non-uniform external field. Now, when I say external field, definitely the field is due to the source charges, but there is no need of showing those source charges when we are representing the electric field which is external. Fine? Okay. So, how to represent or how to draw a non-uniform electric field? Now, what is the meaning of this? That the electric field has different values at different points. That is the meaning of non-uniform electric field. Fine? Okay. How do I represent it? I represent it by non-parallel lines or curves, or even if I represent it by parallel line, non-equidistant parallel lines. Non-equidistant parallel lines. Right? This is the way of representing a non-uniform electric field which is external other than the dipole. How do I represent it, or how do I draw it? I can draw it like this. Yes, I have drawn some lines which are not parallel to each other, also not equidistant from each other also. Okay, I can also show it like this as curves. Fine. I can also show them as this method, curves, or I can also show them as approximately. Now you can see that the directions are also different for the electric field lines, and the density of the line at each place or each spot or each point is also different. Suppose if I consider the point A here and B here, at the portion of A, the electric field lines are more. So the electric field is more. Compared to the portion at B, electric field lines are less. So electric field value is less. So what can I say in this case? E1 at the point A is greater than E2 at the point B. The value is not same for every point in the given surface for the electric field. Then we can say that electric field is non-uniform. Even here also, these are curved lines. I can draw one closer to this, one far away from this. All these are field lines which are not parallel to each other. They are not equidistant also. Say that this portion is a non-electric field portion, a non-uniform external electric field. Fine. Here also the same thing. Here you can see very easily, suppose if I put a point A here and I put a point B here, definitely the electric field at the point A will be greater than electric field at the point B, because here the lines are more and here the lines are less. So for a non-uniform external electric field, we have to understand that they are represented by non-parallel lines, they are represented by curves, they are represented by equidistant parallel lines, and the density of the lines is not same at all the places of the surface. These all points we have to Remember, they can be represented by curves also. Okay. Now, when we want to represent it as a single field, then do we draw all these together? No. How do we do it then? We just draw one single arrow or a single line representing the increase in the electric field value. What does this arrow say? That the electric field value is increasing from here towards the arrow's direction. This is the meaning. When you say this is a non-uniform external electric field, and if I have represented it as an arrow like this, it means that this is the direction of increasing electric field. Fine? Okay. So for the direction of decreasing electric field, this way it is increasing, but this way it is decreasing. In this diagram also, in this way it is increasing and this way it is decreasing. The value, suppose if I say the value here is E1 and here the value is E2, then in this case E1 greater than E2. Fine? And here if I say this is the value again E1 and here the value is E2, here I say E2 is greater than E1 because the increasing side is the arrow side. Right? Okay. So now we have understood how to represent the non-uniform external electric field. Now, whenever such words are spoken, don't get confused with so many words. They can just say non-uniform field. It can be just told as non-uniform external electric field. It can be just told as non-uniform field. All mean the same. It only means that the value of the value of electric field is not same at every point of the given surface. That's it. Fine. So now let us place the case 1 in which we are placing a dipole parallel to the non-uniform external electric field. Fine. So, as I said, representing the electric field in this way means that the value of the electric field is increasing electric field in this direction. Fine. Again, if I represent it by another line also, this is also increasing. Fine. Okay. Now, in this increasing electric field, I have placed a dipole represented by a positive charge and a negative charge parallel to the electric field's direction. Again, revising the direction of electric dipole is always from negative charge to positive charge, and it is a combination of negative charge and positive charge with a distance of 2a between the two charges. Fine. So as you can see, the direction of electric field increasing is represented like this, and this dipole is kept parallel to the direction of the increasing electric field. Now we should understand whether force is there, net force is there, torque is there, what is there? Is it there or is it not there? That is our task for a electric field which is non-uniform. So first let us consider whether force is there or no. Okay, so let us represent this side by E1 which is increasing, E2 which is less. So we have taken a condition in which E1 greater than E2. Fine. Okay, if E1 is greater than E2, charge Q is same this side, charge Q is same that side, but the polarity is different. So this side I will get electric field. So for F1 I can write Q E1, which is our formula for force is equal to charge multiplied by the electric field, and for F2 I will get negative Q electric field E2, where negative indicates that the direction of force is opposite to the direction of electric field. So now if I add these two values F1 plus F2, then I will write QE1 minus QE2, which is equal to Q common E1 minus E2. I have already taken E1 greater than E2. So I will get a positive value for the net force. So do I have a net force? Yes. What is its value? Positive. So what will be the direction of the force or the motion of the dipole? A translatory motion in the increasing direction of the electric field. So in this direction, the P arrow or the dipole will move in the direction of the increasing electric field. So let us represent this as the direction of increasing electric field, this as the translatory motion of the dipole. As I said, it will move in the positive direction because our value is positive. Fine? Okay. So the translatory motion will be seen in the dipole in the positive direction or in the increasing direction of the electric field. So what should be in your mind? When I place a dipole in non-uniform electric field, it will definitely experience a force, a net force will be experienced by it. Depending upon the values which we have considered, it can go in the direction of the electric field, increasing electric field, or it can go opposite to the direction of the electric field. Okay. So now we consider case 2 in which we place the dipole anti-parallel to the increasing electric field. We already know it is non-uniform and now we have taken increasing electric field. So how do I represent an increasing electric field? Like this. Okay. This is the way I put the increasing electric field. Fine. In that I have to place the dipole anti-parallel. Now what is the meaning of anti-parallel? Theta is equal to 180 degrees between the dipole and the electric field. Similarly here theta was equal to 0, correct? Between the dipole and the electric field. So now how do I place it anti-parallel? If E arrow is like this, then this is the negative charge, this is the positive charge. So I join them, this I have made the dipole. Now as we know, the direction of the electric field is always from negative charge Q to the positive charge plus Q. Fine? Okay, so the direction of the electric dipole is opposite to the direction of the electric field. Theta is equal to 0, anti-parallel. All these words should come as a combination with each other. Okay, one word used will automatically make you understand that theta is 180 between P and E. Theta is 180, so E and P are opposite to each other in their direction. These all should be there in your mind. So I have placed a dipole anti-parallel to the increasing electric field, which is non-uniform. Fine. Okay. So this direction is of increasing electric field. Fine. Okay. Now let us see what will be the direction of force. Whichever direction of force, that direction will be the motion of the particular dipole which we have chosen. So let us first consider what is the force. So for that, what is the value of electric field here again as before? E1. Here it is increasing. So here it is E1, which is more than E to the side. So I have taken the condition E1 is greater than E2. So let us write F1. What is the value of F1? This side negative Q is there. So negative Q E1. Correct? This side positive is there. Charge. So positive Q E2. So what is the net force? Net force is F1 plus F2. What should I write here? F1 negative or a negative Q E1. And what is F2? Positive Q E2. Let me take common, Q common. So I get negative E1 plus E2. Already I have considered E1 is greater than E2. Correct? So what happens here? If I write here, if E1 is greater than E2, then negative E1 plus positive E2, I will definitely get a negative answer here. For the force, I am going to get a negative answer here. That means the force is in a direction opposite to the electric field, this side. Agreed? Again, I have added them and I have got in the bracket E1 negative plus E2. That means value of negative E1 is greater than E2 because E1 is greater than E2. Fine. So whatever answer I get, I am going to get in negative. That means the force is in a direction opposite to electric field. That is the meaning. Fine. Because as already discussed, if this side is negative, it means that both the vectors are in opposite direction. So if force is in this direction, then the dipole also will move in this direction. So let us represent it. What is the representation? As per we have taken E, this is increasing electric field. What we have got? Force. This negative direction, correct? Opposite to the increasing electric field. So dipole will also move in this direction. So this is the direction of force, decreasing electric field, and the direction of electric field which we took is increasing electric field. So finally what we will write? What is the result? E is in increasing electric field. Force is in decreasing electric field. Force is going towards decreasing electric field. So dipole will also go towards decreasing electric field and net force is there. That's why the dipole will have which type of a motion? Translatory motion. Okay. So in both the cases, we have, this is about question. When we place a dipole in non-uniform electric field, does it have a translatory motion? Yes. When we place it in uniform electric field, it did not have a translatory motion because F net was equal to 0. Here F net in both the cases is not equal to 0. So translatory motion will be there. How? If I place both dipole and electric field parallel to each other, translatory motion will be in the direction of the electric field for the dipole. If I place dipole anti-parallel to the electric field, increasing electric field, then the motion of the dipole will be opposite to the direction of the increasing electric field. So translatory motion will be there for both the cases, whether anti-parallel or parallel. So, is torque there? In this case, it won't be there. Why? Torque happens due to couple. Otherwise, in some orientations it will be there. But in this case, we have taken theta is equal to 0, theta is equal to 180, tau is equal to PE sine theta. If I substitute theta is equal to 180 or theta is equal to 0, I am going to get tau is equal to 0. If I am going to get tau is equal to 0, then there is no torque, provided my theta is equal to 0 and theta is equal to 180. If my theta is not 0 or 180, some other value, and I have placed it in non-uniform electric field, tau will be there, depending upon the orientation. So depending upon the orientation, torque will be there when I place a dipole in a non-uniform electric field. If theta has some other value between 0 and 180, torque will be there. If theta is 0 or 180, torque will be 0. It will not have a rotatory motion, right? And force for both the cases will be there. So this is what are the points which you have to remember, that when I place a dipole in non-uniform electric field, the force is non-zero, torque is also non-zero. Because force is non-zero, the dipole will have a translatory motion. Because the torque is non-zero, the dipole will have rotatory motion also, provided theta is between 0 and 180, torque will be there. If theta is 0 or 180, then tau is equal to 0. When is tau equal to 0? For this case, tau is equal to 0 if the orientation is theta is equal to 0. Parallel, theta equal 180, anti-parallel. These are one markers. Okay? Remember them as a complete package of whatever is written here. Force is there? Yes. Tau is there? Yes. Tau is not there when? When theta is equal to 0 or theta is equal to 180. Either you say theta is equal to 0 or parallel. Theta is equal to 180, that is anti-parallel. Who are parallel? P and E. And who are anti-parallel? P and E. This is what you have to remember. Fine. So I will just move now. You can take a screenshot of what we just did. Okay. And learn it as it is. Fine.